Hi class, for this sections we want to talk about the definite integral. So in 5.1 we saw this limit right here, the limit of the sum from I to n f of x1 star delta x. This time we learn the definition of a definite integral. So first, f is a function defined from a to b. Then we divide the interval from from a to b into n subintervals of equal width. Delta x equals to b over a divided by n. This is similar to what we did in 5.1. But this time we actually state the definition, right? So you see right here, we let x naught equals to a and so on. Now, the definite integral is gonna be like this. So you see right here, this is the integral sign from a to b f of x. That's pretty much just the limit of the sum of f of x1 star delta x. Now, um, if this limit, if we do have the limit and gives the sample values of all possible choices of the sample point, if we do have it, then we call f integrable on a, b, on the interval a, b. Now, there's a couple of things I want to point out. So you see right here, this is the integral sign. So it's like S stand for sum, right? And then we have the integrand in here. We have the lower limit and we have the upper limit. This whole process is called integration. So if I give you an example, I call integrate. This is what you have to do. Now, this whole thing right here is a number, so it does not depend on x. In fact, if you put f of y here, then it's going to be dy, f of r, then it's dr, and so on. The sum, f of xi star delta x, is called the Riemann sum. It's the sum of area of the rectangles. The integral from a to b f of x dx is the area under the curve right here. Okay, so you see right here what I have, because it's above the x-axis, so it's positive. If it's below the x-axis, then it's gonna be negative. So the definite area is the net area, is a1 minus a2. Okay, now these are the theorems we have to memorize. So f has to be continuous on AB, f has only finite number of jump discontinuities, then f is integrable on AB, which means the integral from a to b f of x dx exists. And then we have the theorem, so the integral is the limit, just like the definition earlier, right? So delta x is going to be b minus a over n. Xi is a plus I delta x. This is what we did in 5.1. Now we just put everything in the definition. So example 1 is straightforward. They just want you to, they give you the limit of the Riemann sum, and they want you to rewrite as the integral on the interval. So by theorem 4 right here, I'm just going to take that. A is 0, B is pi, and then I put the function in here. Okay, straightforward. This is going to help you to evaluate the integrals. So if you take what do I mean by this is actually 1 plus 2 plus 3 plus 4 plus 5 and so on. So this is the formula for it. I square is 1 square plus 2 square plus 3 square and so on. So you're gonna get this one right here, I cube and so on. Now let's take a look at example 2. They want you to evaluate the Riemann sum for this function right here, taking the sample points to be right endpoint, and they give you a is 0, b is 3, and n is 6. So what we have is six subinterval. So you see right here, n equal to 6. We have to figure out delta x, which is b minus a divided by n. I plug it in, turn out is 1/2. The right endpoint, which is 1/2, and then 1, we keep adding 0.5, right? We keep adding 0.5 to get the points. Now, the R6, the right endpoint, so I pretty much just plug it in. So f of 0.5 delta x plus f of 1 delta x, f of 2.0, and so on. And then I just use a calculator for it. Now, I have to make these notes because f is not a positive function, and then the Riemann sum is not the sum of the area of the rectangles. You see right here, this is a Riemann sum. So what is it? This one represents the Riemann sum represents the sum of the green areas here, the green rectangles, minus the sum of the negative one, the orange rectangle. So this is positive, this is negative. For B, they're asking you to evaluate from 0 to 3 with that function. Okay, so we have 0 to 3, and we have the limit. We write the limit based on theorem 4, and I pretty much just plug it in. First, you need to figure out delta x, x not equal to 0, x1 equals 3 over n, and then so on. So xi is 3i over n. So I plug it in. So this is a function, this is delta x. Now taking the limit, so I just factor out 3 over n right here. I have the sum inside, the Riemann sum, right? So you see right here 3i squared. So I have 3 over n right here, and then I pretty much just simplify everything. I multiply, I simplify it. Okay, hopefully you recognize it. And then from here, just do more algebra. And then I3 right here, I'm using the formula to get this part right here. So I3, I'm using the formula is n times n plus 1 over 2 squared, right? Let me go back. I'm talking about this one, okay? All right, so moving on. I, that's a formula for I. So from there, like I said, more algebra. Okay, I do a lot of calculating, so simplify and square, I multiply it out. And then I reduce with n right here on the bottom. So it's a lot of simplification that we have to do. So it's just a lot of algebra here. Okay. All right, moving on to example 3. So example 3, they want you to set up an expression for the integral from 1 to 3 e to the x power dx as the limit of the sum. So first, you need to recognize which is which. So f of x is e to the x power, a is 1, b is 3, and then we figure out deltas b minus a over n, which is 2 over n in this case, right? And then I keep on calculating x0, x1, x2, x3, so I can get to xi. So by theorem 4, we pretty much just use the integral, take the limit of the Riemann sum, and then we ended up right here. This is delta x. This is the function, right? And then I just plug it in, right? Plug it in, f of that, the function is e to the x power. So I got to this part. All right, let's take a look at example 4. So example 4, we want to evaluate the integrals right here, part A is from 0 to 1, the square root of 1 minus x squared. What is it? Hopefully you recognize is this part right here. Okay, it's part of a circle, right? So we take the square root. Anyway, so y is square root of 1 minus x squared. This part right here is greater than 0. Now, hopefully you still remember that x squared plus y squared equals 1 is a circle with the radius 1. So if I take the square root, it's a quarter of the circle. You see that? A quarter. So if I draw the whole circle, this is just a quarter. Now, what is the area of a circle? Pi r squared, right? So 1/4 pi r squared. So that's how I got pi over 4. Now for this one right here, you have a linear function right here, a straight line, okay, from 0 to 1. So this one right here, you can see that we have a1 for the positive and a2 for the negative. So as you can see that we have two triangles, and you subtract a2 from a1. So what is the sum of a triangle? Half base times height. Base 1 times height 1. Half base 2 times height 2. And then I just use base height, base height, and that's how I got the formula, and that's how I plug it in, and that's how I got the number. Okay. All right, midpoint rule. So the midpoint rule, pretty much using xi bar is the midpoint. We did that in 5.1, so this is not something new. So for example 5, we want to use the midpoint rule for n equals 5 to approximate the integral. We did this in 5.1. So you see right here, I have the endpoint. Okay, first of all, same thing. We calculate delta x. We get the endpoint, and we get the midpoint. So pretty much I just get the midpoint of these, the midpoint. So that's how I come up with 1.1, 1.3, 1.5, 1.7, 1.9. And then from there, I pretty much just plug it in using the definition. So delta x and f of 1 plus 1 times 1. I'm sorry, f of 1.1 plus f of 1.3. And then from there, I use the function right here, plug in the number, and then I use a calculator for it. Okay, so f over x greater than 0 for x in between 1 and 2. So the integral represents an area. Okay, and then we have some properties of definite integral right here. Now, you see, if you want to integrate from b to a, it's just the negative, the opposite of from a to b. If a equals to b, then delta x is going to be 0. Okay, so the integral, when you integrate it, is going to be 0. Okay. All right. So make sure that we assume that f and g's are continuous function. Okay. Right here we have some properties of the integral. You see right here when we have just the constant, c is a constant, and if you take the integral, it's really simple. It's just c times b minus a. If you have the integral of the sum, then it's going to be the sum of the integral. C, the constant c, you can always take it out of the integral. And we have it for subtraction as well. All right, so example 6 right here, I want to use the properties of integral to evaluate this. So you see that first of all, I can break it into the sum of two integrals. And then we know that 4 is just a constant. So I'm just take 4 times 1 minus 0 times b minus a, right? 3x squared, I can take out the 3. X squared from 0 to 1, the integral, we did it. In example from 5.1, we know the result is going to be 1/3. So 3 times 1/3 is just 1. So altogether, I get 5. 4 plus 1 is 5. Okay. Um, moving on, you see right here, moving on to this property. This property, if you have from A to C, that and then you have from C to B, that's pretty much when you add them up, that's pretty much taking the integral from A all the way to B. Okay, so right here, I want to take the integral from 0 to 10, and I know it's going to be 17. From 0 to 8 is 12. So I'm asking you, what is from 8 to 12? So we pretty much just subtract, right? Because this is the sum of, so this is right here is the sum of this one and this one, okay? And then I have more properties here for you, okay? So these properties are straightforward. Example 8 right here, we want to use this particular property to estimate the integral. So we need to find a boundary, right? So f of 0 is 1. Let's call it the big M, which is the absolute max. This is the absolute min. F of x is decreasing on 0, 1. The function is decreasing from 0, 1. So if you graph it, you will see that it's decreasing, right? And then we're using this one right here. You see right here, f of x is bounded by m and m, little m and big M. So I'm just using this. Okay, I'm just using this. And then from there, I know that it's bounded by 1 over e and 1. Okay, so I pretty much just use this one right here and plug it in, the function.